to continue. Yogesh, I think it's time for you. Thank you.
Sure. Thanks a lot, Lakshmi, and good afternoon, everyone. Thanks for joining us today in this information session. Let me just get my pointer up. Great. So I had the Dream Lab at the CTS department at IISc. And just to briefly give my background, I got my PhD in Indiana University, did a postdoc at Microsoft Research at LA and San Francisco, was a research faculty at USC. And I've been at IISc for the last 8 years or 9 years or so. And at IISc, I've had a very fruitful time, enjoyable time, and had a lot of good research that happens. And all of this is thanks to a great bunch of students that we have in the lab. Right? So all due credit to them. So this is our current lab members. We have about 6 PhD students, some of them jointly advised, and about 4 masters course students, along with several project staff and postdocs. And we've had a long list of alumni. 20, 25 students and staff have graduated from our lab in my time here at IISc, and they've gone on to some really top places for their future careers. Right? But what do we do, right, in the lab? So one way to think about it is that we want to understand how we can make use of distributed systems, right, in order to better run or operate large-scale applications. And obviously, one of the largest scales of applications that we currently encounter is machine learning applications. So a lot of our recent research has been on trying to understand how distributed computing systems and data systems can be used to scale ML applications to really large sizes and how to run them efficiently. Right? So what do we mean by distributed systems? It's a very heterogeneous mix, right? It could be cloud computing, like what Lakshmi mentioned earlier on. It could be public clouds, private clouds, virtual machines, functions as a service, and so on. It could also be at the other end of the spectrum, edge devices, right? Starting from a smartphone to a Raspberry Pi to NVIDIA Jetson kind of devices, which are accelerated edge devices with a low-end GPU. Or it could even be, as we'll talk about, drones as a computing platform, right? So they have mobility, sensing, and computing and communication on board. Or it could be more mundane commodity classes. So there's a wide flavor of distributed systems that we deal with in our lab. And when you talk about ML applications, and I'll talk a bit more in detail about some of these projects, this again spans a wide spectrum. So starting from looking at how do you do GNN training at large scales, how could we design software platforms for that, to federated learning on edge devices, to even video inferencing pipelines, and NoSQL databases for video management and so on. Right? So the variety of, because ML is pervasive, even if you don't do research in ML, right, you are bound to touch machine learning in some manner or other as part of your research, and that's what ends up in our lab as well. Right? But if you look at it as a overall stack, right? So we are cognizant of the hardware layer, but we don't work at the hardware layer. We are above the hardware layer for sure. But we start everywhere from these software platforms or software systems that interface with the hardware and go all the way till the algorithms and applications that you might design on using these software platforms, and the applications themselves that are going to be making use of these algorithms and analytics in order to run on the software platform. Right? So like I said, the edge devices, the computing devices could be plentiful. So some of the platforms that we work on are graph platforms. We work with NoSQL databases. We work with streaming platforms. We work with things like functions as a service and microservices platforms and so on. So that again is fairly a wide spectrum of interest. But at the end of the day, you can think of these as, if you've heard of things like TensorFlow and Hadoop and Spark and so on, or even PyTorch, right? So those are actually platforms. Those are actually platforms that help you, let's say, do large-scale data management or data analysis or machine learning and so on. So if you're used, and I'm sure many of you would have used these platforms, right? You don't think of these as platforms. You think of them as a framework or a tool or library or whatever it is. But behind the scenes, if they help you make use of large-scale computing resources without you being really worried about how they work, that's really the platform. But we, in our group, we actually care about how these software platforms work, and we try to improve and advance them. The other is in terms of abstractions and algorithms. Right? Right? So here again, you have to think about how best can you sort of think about distributed algorithms, because you might all have come across algorithms in many, many different forms in your prior life. But the moment you have a collection of distributed resources, you're not programming for a single machine. You're designing algorithms or writing programs for a large collections of machines. So you have to rethink how you approach designing these algorithms. At the end of the day, all of these are motivated by very practical applications. So anywhere from Internet of Things to smart cities to even drone-based applications and so on are all in our purview. Okay, so thanks a lot, Yogesh, for letting me know that I haven't shared my screen. That's okay. All right, so apologies for that. So let me just do a quick recap. So that's me, Yogesh. That's my background. And that's the set of students that we have in our lab. Most of them are master's students and a handful of, most of them are PhD students and a handful of master's students and several project staff as well. And alumni at top places, from Microsoft, Google, and some of them have gone on to do PhDs at places like our masters at Stanford, CMU, and so on as well. So systems for ML, how can we make use of distributed systems, which include cloud computing, edge computing, commodity clusters, and so on, and also various types of ML applications. Right? So GNN training, federated learning, video inferencing pipelines, video data management on NoSQL databases, and ML ops as well. All right, so this is the stack that I talked to you about, which maybe you can sort of appreciate for a minute before I move on in the interest of time. So this sort of gives you some broad context, hopefully, in what we do. Right? So hardware up all the way till the application is all of interest to us, as long as the key theme over here is distributed. Like if something can be run on a single machine, we are not very interested. If it exceeds the capacity of a single machine, or if the data itself is designed, as for example, if you have things like Internet of Things, data itself is going to be coming from very distributed sensors and so on. Right? So you don't have the choice of doing centralized. Right? So that's the space that we are interested in. Right? All right. So a couple of sort of ideas to sort of highlight over here. Internet of Things and edge computing are sort of fast complementing cloud computing, which Lakshmi already talked about. So here you're looking everywhere from your Raspberry Pi class devices to your GPU-based workstations, the plenty of fog, and even accelerated edges and so on. So if you think about your computing paradigm right now, I mean, each one of you is carrying a smartphone. Right? That's an edge device, right? And if it's a high-end smartphone, it probably has a GPU or a TPU accelerator as well, right? So each one of you is a walking edge device, right? And all of you are sort of connected to the cloud, meaning this whole Teams itself, sessions being enabled by the cloud, right? So distributed computing is all around us, right? So there's no escaping the fact. So the question is, how can we make the best use of it, right? And gone are the days where you can just program for a single machine and your job is done, right? So any sort of algorithm or application you'll be designing, a modern algorithm application, has to make use of such large-scale computing resources, either on the cloud or on edge devices. Right? So the question is, how can we best make use of potentially thousands of such edge devices plus cloud intelligently? Right? So that's the systems perspective. You have this opportunity of all these distributed resources, and from the application side, you have all these ML-based applications that are sort of fast becoming important. How can the two meet in the middle, and you can make some substantial research advances to make use of that? Let me give you a couple of examples of work that we have done in the past, but I'll quickly shift over to some of our current and future-looking problems as well. Because if you are shortlisted and you sort of get an offer and you decide to join our lab, those are some of the kinds of problems that you might yourself be working upon, right? But just to give you some sort of recent history, this is some work that Akash Kochari, who's sort of soon to be graduating PhD student in our lab, was working in terms of how can we make use of distributed edge resources. So nowadays, if you go to any major city, you'll start, you'll see your traffic cameras and your surveillance cameras and so on, which a city has installed, right? Bangalore itself is in the process of deploying thousands of such cameras, right? So now the question is, what do we do with this? So for the most part, these are just sent to some hard disk stored there, and very rarely you might have someone go and take a look at it, right? So they're not actively used. So one of the questions that we try to answer is that can we make use of such real-time video streams from potentially thousands of cameras to perform some meaningful application. In this case, we thought of a tracking application, which is very easy to understand. Let's say you have a stolen vehicle or a lost child, and you want to sort of track that vehicle or that person through this camera network. Right? One thing to say is to sort of say that, hey, I'll start analyzing all 1,000 video streams and do some object detection and so on. So there's a lot of such fancy DNN models that are already there to do this sort of analysis, right? But we are less interested in that part, right? Because the requirement for you to sort of run such DNN inferencing on top of thousands of cameras is going to mean that you will have to have thousands of GPU resources available with you, which is intractable. Right? So we wanted to look at it from a systems perspective, more smarter perspective. Right? Can I be smart about which cameras I even start examining? Right? So why do I have to look at all 1,000 cameras in the city if I have an approximate idea of where the person was last seen or the vehicle was last seen, right? And this could even be very well back in time if you got historical data available, right? So can I go and have some kind of a spotlight algorithm, right? Where I localize my search to a certain region and maybe identify that individual within a specific camera, right? And if I hit any blind, and then sort of keep tracking that person across adjacent cameras, right? And in case the person gets into a blind spot, I start increasing my search radius proportional to the time for which the person has been lost. And eventually, hopefully, I'll recapture them as part of a different camera, right? And then I do that. So one of the contributions that we had was in terms of a dynamic algorithm, right? A distributed and dynamic algorithm that will help you scope the search space so that you can do tracking using minimal resources, right? So you don't have to look at 1,000 video feeds and have thousands of GPUs, but only look at maybe a couple of tens or at most hundreds of such sort of video feeds, right? The second part is about doing this on the edge, right? Because you cannot afford to bring in even hundreds of video streams to a central location, right? So the bandwidth is just going to kill you, right? So you have to make use of potentially edge computing available, co-located with the actual sort of camera itself. Many of these cameras come in with sort of embedded processors or even sort of low-end GPUs and so on. So can you push some of the analytics over there? And there again, there are interesting issues of how do you do various kinds of scheduling of tasks across these edge resources, and how do you sort of optimize the network data transfers and so on, right? So bottom line, so in this sort of problem, we were looking at how do you do a trade-off between the speed of detection, the accuracy that you get, as well as the active number of cameras that you can support. And so we had this kind of a tuning triangle. This sort of work got published at TPDs, the top journal in this area, and also won the IEEE Scale Challenge and got featured in HCM Tech News as well in one of their cover stories. Another example of distributed computing, which we have worked on and we continue to work on as well, is about how can you make use of fleets of drones, right, in order to sort of accomplish various tasks, right? So, and if you think about drones, these are essentially flying computers with sensors on board, right? So drones have mobility, drones have sensing capacity, and drones have computing on board, right? So one of the problems that we looked at over here, which got published at Infocom, again, one of the top conferences in this area last year, is if you have a fleet of drones, right, and you have a set of observation activities that you have to perform. Let's say a traffic police say that, hey, I want to observe the traffic at so-and-so junctions in the city during the peak commute hour, right? So I want to sort of go collect data from these video data from these locations, but I also want to do some kind of analytic. Let's say I want to count the number of vehicles that flew that flowed through a junction within a 5-minute period. Right? So you have a set of tasks that are given. Right? How can you schedule a collection of drones to visit these waypoints, right? To collect data at the appropriate time, and also perform onboard analytics on top of the drone, not just bring it back to the depot and run it externally, but do it on the drone itself, right? So this essentially ends up being a mix of a traveling salesman problem, a classic graph problem, combined with a job scheduling problem, because you have to do analytics on both the drone, and the drone has limited computing capacity, right? It may not be possible for you to do all the analytics on the drone. Some of it might be done on the drone, some of it might have to be offloaded. How can you actually sort of balance such scheduling problems? So that was something that we addressed. And here again, we made use of actually real drones as well, and we did some real world prototyping to validate some of this work. And some of the work on the drones is actually something that we collaborate with Art Park, it's like a UAV or Autonomous Systems Innovation Hub at IISc as well. A third problem that we have worked till recently, and that got published in ICD, one of the top data systems conferences 2 years back, was on temporal graphs. Right? So here we've looked at if you got large-scale, large graphs, right? So like social network graphs or even transportation graphs and so on, right? And you want to run sort of graph algorithms on top of that, right? So like Dijkstra's or spanning tree or clustering and so on, right? But the added twist is that besides the graph themselves being very large, like billions of edges is fairly common for us. And these obviously won't fit in single machine. Your memory is just going to blow up. It might take days to complete, right, on a single machine. So you have to do distribute. But the added twist over here is that many of the real world graphs are dynamic in nature, right? So a road network is not static, right? The traffic flow keeps changing minute by minute, right? Likewise, a social network is not static, right? But many of the graph algorithms have been designed for static graphs. So the question is, how can you design algorithms for dynamic and temporal graphs, and B, how can you design sort of software platforms or frameworks, right, that can help you implement such graph algorithms, dynamic graph algorithms, in a very easy manner so that you can make use of distributed computing. So something that might take days to complete on a single machine could run a lot of minutes on a cluster of machines, but without you having to completely, meaning you have to spend weeks together implementing that algorithm on for a distributed setup. So when you ease the development process, the algorithm design process, while also getting efficient execution. Right? So that's some work that we have done in the recent past. So what's the common theme across these? We've talked about everything from graph algorithms to sort of drones to video analytics. The common theme over here is that the applications might be diverse, but they all need to make use of distributed computing. Right? So that's where things come together. And just to sort of give you a flavor of some of the practical or social impact of some of our recent work, especially during COVID, one of the silver linings is we took some of our prior research, especially in the context of temporal graph algorithms, and we actually put it to use in the context of contact tracing for COVID. Because if you think about it, a contact tracing is nothing but a temporal reachability algorithm. Right? So we were literally able to take one of the algorithms from our paper and implement it on top of a contact graph for data that we collected from within the IISc campus through a contact tracing app called Go Corona Go, and actually get results out of that. So, so this is an example of research having practical impact and sort of helping sort of mitigate things like COVID. But we also have projects like how do you do sort of better water, efficient water management, water supply within Bangalore city. We are working with the city to come up with various kinds of graph algorithms for optimizing water flow within the city, safe water distribution. We're also looking at air quality monitoring. Some of the IoT work and even some of the drone work could be employed over here. How do you low cost air quality monitoring within the city so that you can sort of better improve the quality of life for citizens, and also do data-driven data-driven policies for mitigating pollution and so on. So several of our projects do have a practical impact or a social impact as well, not just a research impact. Right? So let me talk about a few problems, right, that are sort of either in the gestation stage or sort of we have probably spent maybe a year or so working on and are actively looking into. But there are a lot of open problems, right? So oftentimes research, if you come up with a research problem, it's just a starting point for a series of interesting problems that you can branch off into, right? So one problem that we're looking at, again, driven by our prior work on large-scale graph processing, right, is looking at training graph neural networks, right? So graph algorithms themselves are fairly complex, and DNA training can also be very computationally costly, right? But if you blend them together in the form of graph neural networks, which are sort of very popular in the context of everything from sort of social media recommendations to sort of looking at purchasing behavior within e-commerce websites and so on. So this has umpteen number of complex problems from a scalability as well as sort of algorithms perspective, right? So here some of the questions we're trying to answer are, how can you sort of design graph platforms, distributed graph platforms, so that you can take, you might have, as an ML researcher, you might have come up with a GNN model, but how do you take it and map it onto a software platform so that you can run it at scale, right? So you don't have to worry about, you as an ML researcher can only focus on the ML part, but as a systems researcher, our group will give you the software tools to run this at scale, and also the algorithmic tools to actually maybe redesign your ML model or a GNN model to operate on a distributed systems, right? So that's where the ease of abstraction comes in, right? And how can we actually optimize the execution? Because when you look at graphs, they're very irregular in nature. They're not very sort of evenly distributed across different machines and so on. The communication patterns are going to be very different across clusters. So how can you put all of those together in terms of reducing the time taken or scaling the size of the graph on top of your available distributed sort of resources that you have, right? And so those who are interested in graph algorithms, distributed algorithms, software systems, and so on, right, would be a good fit for sort of this kind of a problem. Another example is on federated learning. Here we are looking at how can you make use of potentially hundreds of thousands of accelerated edge devices to train federated models. The idea behind federated learning is that you have your local data on various devices, such as your smartphone or Alexa and so on. The device itself would train a local model, but the local model will be sent to a central server in the cloud. The cloud would actually do an aggregation of this model, right? And this will happen iteratively between the edge and the cloud until everyone converges to a single global model. Right? So this gives you better privacy, but this can also sort of potentially reduce accuracy and increase the training time, right? So the question for us is that, can we make this entire training much faster by having very insightful understanding of how training happens on the edge? Because an edge device, like an NVIDIA Jetson device or an accelerated edge device, has a very different behavior, system behavior, compared to, let's say, a workstation or a server, right? So, and energy efficiency also becomes a key issue, right? So can we, how can we optimize such edge devices to train DNN models, right? Because training DNNs on the edge has not been explored. Inferencing on the edge, very common, right? And likewise, if you're doing a federated learning, how can you actually pick and choose a right subset of edge devices to sort of accelerate or sort of speed up the training that you perform, so that you can minimize communication between the edge and the cloud, you sort of get right representative data across the different edges, make use of their computing capacity and so on, right? So all of these become very important systems questions that you have to answer for you to hasten the convergence of your federated learning algorithm. So those with an aptitude for operating systems, hardware, accelerators, scheduling algorithms, and doing large-scale experiments would be well suited for this. Okay? Another couple of examples. So one is on, we have active projects with respect to managing large-scale UAVs. Like I said, these are flying computers as far as we are concerned, with mobility, sensing, and computing. And these are being used anywhere and everywhere, right? So you're not going to find self-driving cars in India, but UAV fleets, both the policy and the sort of industry itself is moving actively into this. But for us, this is a distributed systems problem, right? So how do you have drones collaboratively perform various tasks? So that's a classic distributed systems problem, which we'd like to take a shot at, right? How can these be used not just for logistics and supply chain that the industry is interested in, but even sort of helping out visually impaired people in the Indian context, rather than having seeing eye dogs? How can a drone help people who are visually challenged navigate a complex city, right? And likewise, things like cloud and 5G are going to have a big impact on drones. So how can you sort of tap into those resources as well in order to solve such distributed problems, right? So everything from distributed scheduling to those who are interested in the hardware, software of drones, communication networks, all of these are sort of interesting sort of skills to have if you're interested in this space, right? And lastly, for a problem definition, we are looking at machine learning life cycles, right? So meaning we have a lot of ML researchers who are sort of focused on the ML part. A lot of they take it, they deploy it. But the people who actually build models and people who actually use the models are highly decoupled. Right? And in typical industry, this entire thing is actually a life cycle, right? So everything from collecting the data to training a model to hyperparameter tuning to deployment where you infer in large scale, and then sort of figuring out that you have to retrain because the model is having a skew and so on. All of this is a very long life cycle, right? So now we need a way to manage this end-to-end life cycle for a model, right? So that's something that there aren't the right set of software tools present right now, and we are interested in sort of taking a stab at that. So everything from looking at the entire training life cycle, how do you optimize the deployment and training of such models? How do you collect data and metadata about this entire model's life cycle so that you can even sort of optimize future model training, or you can even guide the development of new models, saying that, hey, these models seem to have worked better in the past. Why don't you start with that as a start, like initial point? And here, people are interested in things like DevOps, Kubernetes, cloud computing, and information management, and so on would be a good fit. Right? All right. One thing I want to emphasize, switching gears, is we are a systems research group. So I've talked about ML as a motivating application domain, but at the core, we are interested in people who enjoy distributed computing, data platforms, NoSQL, sort of operating systems, large-scale sort of software development, and so on. And we are interested in things like scalability, efficiency, and reliability, and performance, right? So we are not an ML research group. ML is a domain that's interesting right now, but 5 years down the line, if ML moves on and something else comes in, we'll still be a distributed systems group, right? And we'll sort of pick the next big application domain that is challenging large-scale computing systems. Right? What do we look for in students who are interested in our lab? The first thing is independent thinking, right? So because that's something that you want from a research degree. At the end of the day, you should be thinking for yourself. I mean, we won't do the thinking for you. I, as an advisor, won't do the thinking for you. I'm just a catalyst in the process. So if you want sort of freedom, right? This is not like a 5th year of your undergraduate or a 6th year of your undergraduate, right? It's the 1st year of your master's or your PhD. So you have to sort of learn to think independently, right? And you should enjoy working hands-on with hardware and software systems. Do large-scale programming is something that we do, designing algorithms. So all of these are essential sort of skills that you should have. And we are a very hardworking lab. We have a lot of computing resources in our lab. We also have fun stuff like drones and AR, VR goggles and so on, which we use for research as well as fun. So we are sort of fairly well sort of provisioned when it comes to in-house lab resources. And we also have a top-notch lab environment that you'll be sitting in, sort of very professional. And our students themselves have gone on to do great things. So everything from having 3 gold medalists for the MTech program in the last few years to multiple PMRF fellowships, best paper awards. So it's almost, there'll be very big shoes to fill in sort of a lab such as ours. And we have active collaborations or grants from various industry folks as well, because many of these problems are things of relevance both to industry, to academia, and to society as well. Right? So we do engage with industry, and students have gone on to sort of top places. And we have a lot of fun, right? So we have, in fact, we have our sports day coming up day after. So we'll have a league match of badminton. We sort of go out for dinners, parties, and so on. But we work hard, right? So it's not just fun. It's also a lot of work, but a lot of fun as well, being in our lab, right? So I'll stop over there, see if there are any questions that you might have, and leave it to the next faculty after that. If there are any questions, just feel free to unmute and ask, right? Or put it in the chat window. Okay, if not, let me see who's up next.
Okay, can I take over, Yogesh?
Oh yeah, so sorry, Satish, I was looking for you on the list. I couldn't find you. Yeah, please go on ahead. Yeah.
Okay.
Thank you.